Okay, does this work? Yeah? Okay, so thank you for having me here in this charming little town. I'm gonna start, I gotta warn you up front that I'm gonna speak pretty fast. You know, I have the tendency to do this. Sorry about that, but I wanna pack as much as possible in this brief 40 minutes. So hope it's gonna be worth it for you. And I wanna start with a very personal confession. My name is Sasha, and I am a very happy user of Elixir. You know, there are a bunch of great stuff that I like in the language itself, a lot of great features, and the tooling around the language, and we have a lot of great libraries and frameworks, and I really feel those things help me in my day-to-day job to focus on the core challenges that I'm supposed to solve. But all this notwithstanding, there is no doubt in my mind that by far the most important thing about Elixir is in fact the thing that exists outside of Elixir and sits below it, and this is the Erlang virtual machine. In particular, I'm referring to the official implementation which we know under the name Beam. Now, Beam is the piece of the puzzle that takes this whole ecosystem and puts it on a place very far apart and makes everything very, very special and different compared to anything else that we have available today. And as a backend developer myself, I feel that Beam is the thing that helps me tremendously with some of the most difficult challenges that I'm about to face, regardless of the particular nature of the project that I'm going to work on. And today, basically, I'm going to try to argue this point, and I'm going to try to explain why do I feel this way. Now, I want to start by saying that Beam, as the runtime layer, is actually not great for every piece of software out there, which is in fact precisely what makes it great in my personal opinion, because rather than trying to be a jack of all trades and therefore a master of none, Beam is built from the ground up with a strong opinion on the kind of software that it is supposed to power. And I call such software a software system. Now, this is the kind of thing that you build, put it into production, start it once, and from that moment on, it has to run continuously, constantly for a long, long time, like many years, maybe even decades. And while it's running, it has to constantly serve the needs of many, many users depending on the system 24/7. It has to do many different tasks at any point in time. So therefore, we don't want really to have a lot of total downtime, total blackouts, preferably none at all. And if something bad goes wrong, the system should be able to detect it and self-heal as soon as possible given the circumstances. And of course, whatever it's doing, it has to perform within some reasonable time constraints, whatever this means for each particular case. So think web backends, web servers of any kind, crawlers, chatbots. In the embedded area, we seem to have a lot of interesting emerging examples. So quite a lot of software falls into this category I'm calling a software system. And then there's a lot of software which is not a software system. And if you're building those other kind of things, especially on some larger scales, like more involved programs, more demanding programs, then very likely Beam is not a hammer to that particular nail. But if you are building a software system, say any kind of a web-facing system, regardless of the business domain, complexity, or scale, there is little doubt in my mind that by far your best option today is any Beam-facing language, precisely because the runtime itself is built for the job. And what this means is the runtime has some properties, it makes some strong guarantees, and in its implementation some trade-offs have been made with respect which are very well suited to software systems at the expense of any other kind of software. And this makes Beam very, very special and unique, and it makes it a perfect tool for the job. And what I'm going to do today is I'm going to cherry pick just a few examples of these properties and guarantees. So not an exhaustive list, just a couple of examples. And I'm going to try to explain why do I find them very relevant in the context of software systems. But before starting, I want to make sure that we're all on the same page. So this is the kind of the idea how I take a look, how I envision a Beam-powered runtime. So say you have your system like implemented in Elixir, and you start it, whether it's on your local development, on the production, the story is going to be the same. You're going to have one operating system process, and this is your own instance of Beam, and in there your entire system is running. So in that OS process, you're going to have a couple of OS threads called schedulers, by default one per CPU core, but completely configurable. There will be some other threads which I'm going to conveniently ignore today. And then you have a bunch of these little yellow boxes, these Beam processes or Erlang Elixir processes, however you want to call them, these lightweight, small concurrent programs. And you're going to have a way larger number of them. This is kind of an idiomatic approach. I usually like to explain it as run different things separately. You want to have different activities in your system be powered by separate processes. And once you adapt to this idea, which is not all that hard, it's quite intuitive in my opinion, you're going to find out that there's a huge potential for complexity even in simpler systems. Like in my experience in smaller systems, you can easily reach for a few hundreds, maybe even a few thousand of processes. Larger systems, tens, hundreds of thousands, millions of those things might be running around during some periods of an increased load. So if you do it properly, you're going to get some great benefits, a lot of superpowers by having a highly concurrent systems. This is a kind of a general idea. Now, of course, scheduler threads are the one actually running those processes. And this is the first thing I'm going to talk about, in particular, how a scheduler does context switching. So a single scheduler will somehow pick one process, and the process lands into the scheduler, and now it has some CPU time for itself. So it can run some beam instructions. Now, during this period, if a process doesn't need CPU anymore, so say it's sleeping, or it's waiting for a message from another process to arrive, or maybe it's waiting for an I/O operation to finish, it's going to implicitly yield and someone else will get the scheduler time. But if a process is highly CPU bound for a long period of time, say computing pi to billions of decimals, it's going to be switched out or preempted, if you will, and this is usually going to happen pretty quickly after the moment it hit the scheduler. Usually in less than 1 millisecond, it's out. I say usually because the actual implementation is not based on time slices and interrupts. So there are some possible scenarios, not very likely, but still possible, where a single process might stay in the scheduler for much longer, like maybe a couple of tens of milliseconds. But those are not very frequent, especially if you pay a little bit of attention. And I'm personally not aware of any kind of Elixir code which we can write that would grab a scheduler and hold on to it forever. So for all practical intents and purposes, we have preemptive scheduler and we have frequent context switching, usually sub-millisecond time. Now what this means for our software systems is a property which I like to call responsiveness. And rather than trying to be all theoretical about it, I'm going to try to showcase what I mean by this. So I have a little site, very simple site, powered by Cowboy and Phoenix, and I'm going to start it now. To make things more explicit and easier to reason about, I'm going to explicitly state that I want to have just one scheduler thread. And of course, I need to start the mix. Okay, let me start the observer and head on to the load charts tab. And now you can tell here that we have only one scheduler thread, and every single beam process in this particular beam instance is going to run on this single scheduler thread. You can tell that it's already a little bit busy because the observer itself is implemented in plain Erlang, and therefore whatever it has to do it on this single scheduler thread. So let me show you the site. Do not expect too much, don't hold your breath here. It's quite simplistic. So I give it a number, and it gives me a sum of the first 10 natural numbers. And if I give it a larger number, I'm going to get a larger sum, which is hopefully correct. I actually have no idea. I have 0 tests there. But it doesn't matter for this particular case, right? So what matters is that the implementation is pretty naive. What I'm doing is I'm iterating from 1 to n, accumulating the sum along the way. So therefore, it's completely CPU bound. There's no I/O, message passing, yielding, and whatnot. So pretty much completely CPU bound. And therefore, if I give it a large enough number, it's gonna consume this scheduler. It's gonna need a little bit more of CPU time. So I'm gonna try with a magical number of 9 nines. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And when I hit this is going to take a little bit longer, and you can tell in the observer that the scheduler is maxed out. But in the meantime, while this thing is still computing, I can go in another tab and I can enter some numbers and I can get my responses. Back there, this thing is spinning and now it has computed. Now what you just seen is we had a long-running CPU busy computation. And while this was happening on the single scheduler, I was still able to serve other requests pretty quickly. And those other requests didn't really disturb the long-running one. I mean, they did, but relatively speaking, it was pretty much insignificant. And this is what I like to call a responsiveness. Let's talk a little bit more about this. So let's say that you have a web server somewhere in production on a machine with a single core, and we have 5 tasks pending, like 5 requests we need to serve. All of them CPU bound. So the first one takes 10 seconds of CPU time, which is quite intensive, but as you have seen, still possible. We have 4 other fairly short ones, 1 millisecond each. Now what's going to happen with beam scheduling is after, roughly speaking, after 5 milliseconds, you're going to serve 4 out of 5 requests, and then you can resume serving T or processing T1. And while you're doing this, you can still take more requests and serve them pretty quickly, assuming they don't require a lot of CPU time for itself. So this is responsiveness, this is a fair scheduling, this is a fair share of resources for everyone, which is what we want because we are serving many different mutually independent users. Now, in cooperative scheduling, and I want to stress that when it comes to lightweight concurrency, this is what most other technologies today are going to give you. What happens is when a task hits the scheduler or a thread or an OS process, it doesn't let go for as long as it needs CPU. So for the first 9,999 milliseconds, no one gets their response. Latencies of all tasks, of all requests, are 10 seconds plus just because you have one super long CPU busy computation. And the thing, this problem exists even if you have multiple threads, because the story it's pretty much the same regardless of the technology which you use. You always have like a bunch of these logical activities that you have to perform. You know, think in thousands or maybe even in millions in larger systems. And you will not have so many OS threads because those things are too expensive. So you will usually have like a small fixed size pool of these threads which are somehow juggling, you know, multiplexing between those activities. And now all you need is just a small fraction of your system which is CPU busy for a longer period of time, and most of your system is on hold. Busyness of one or few leads to paralysis of many or all. And this is not a theoretical issue. I have actually seen this happen in production. I have seen it take the production down. Strictly speaking, it was working, but latencies were so unacceptable that for all intents and purposes, it was as good as dead. Not only have I seen it happen, I have actually made it happen myself. Not intentionally, but by mistake. You know, I made some crappy, suboptimal piece of code. But mistakes happen from time to time, right? I make them probably on a daily basis, you know. And this is a great example of how a seemingly low-level technical property plays an important role in deciding how my mistake plays out in real life. And here, cooperative scheduling amplified my mistake to the point where it took the whole production down. Now, Beam is way more forgiving towards such types of mistakes. You know, like if you have some smaller fraction of your system which requires a lot of CPU, that's not going to disturb a lot of your system because you have this frequent preemption or frequent scheduling, frequent context switches. Of course, if you have a bunch of these tasks, you know, then the thing doesn't hold. You know, it's basic laws of physics. You need this much resources. You have so little resources. You know, but the thing is, as the number of these tasks increases, your performance is going to degrade gradually, right? So you're going to have some window to see that something is off and maybe fix the problem before it actually blows out of all proportions. And this leads me to the second property I want to talk about, and this is the fact that in Beam, your activities are first-class runtime citizens. Now, there are two sides to this story. The first one is that your activities, as I have said earlier, you want to have activities powered by separate processes. So an activity is a process, and this is a runtime thing in Beam. This is a runtime entity, and I'm stressing this because it's not always the case. In some lightweight concurrency implementations, this lightweight concurrency is done at the library level, and then it simply follows that the runtime has no clue about those things even existing. Another part of the story is that these activities or these processes have their IDs. We have PIDs, therefore they have identities. And again, I'm stressing it because it's not always the case. The most notable example is Go, which is based on the CSP concurrency model, and in there your activities are anonymous, your communication channels have identities. In Beam, we have activities as runtime entities with identities. Now what this means, what this gives us, is the ability to manage and manipulate our activities by talking to our runtime directly, even if the activities themselves refuse to cooperate. And I find this very, very important, but I understand that it's quite vague, so I'm gonna do the second part of the demo. I'm gonna head back to this little site and show you the bug that I have here. You're gonna immediately know what the problem is, but let's pretend that we don't know and we're gonna see where it takes us. So if I give it a negative number, this thing is gonna compute forever. So you can tell here that it's spinning, nothing is returned. If I head on to the observer, the scheduler is fully maxed out. I can even close this thing, and it's still maxing out. You know, so we're maxing out on our scheduler when we're burning our CPU. Of course, as I've shown you, the site still works, right? So it's responsive. That's nice. But if I get more of this long-running task, this minus this negative inputs, then at some point I'm going to have a self-denial of service. You know, so assuming that I have some kind of a monitoring and alerting system in place, then I should get some notification that my CPU usage is way off, and I should, as an operation or DevOps, however you want to call it, I should head to the production and understand what goes on before things go really bad. So this is what I'm going to do. I'm going to try to troubleshoot this system, pretending that I don't really understand what the problem is. Now, I'm going to do it in its IEX session, but I want to stress that you can do the exact same thing in the production. You can hook into a running production without needing to restart it, without needing to set some trace flags, or God forbid, redeploy your entire system in some kind of a modified version. And you can understand a lot about your production by talking to your runtime directly about your activities. And this is the main point I'm trying to drive. You don't need to remember every single detail I'm going to do here. The point is that we are talking with our runtime about our activities. This is kind of the main idea. So the question is, who is burning our CPU, right? And obviously it has to be one or more processes. So the first thing I can do is I can list those processes, those PIDs, right? And then I can ask my runtime something about them. So in particular, what I'm going to do is I'm going to ask for a process info, okay, about each PID. And in particular, I'm interested in a property called reductions. or reduction count. So I'm going to keep it very simple and stupid, not completely precise, but sufficient. It's a number. Higher the number, the busier the process is. So it's kind of an approximation, but let's leave it like that. And then basically we need to find the processes which have the highest or unusually high reduction count. So what I'm going to do here is I need to pack this thing in a tuple. So like this. Now I have a list of tuples, each tuple being a reduction count and a process ID. And now it's pretty much song and dance. I have to sort this thing in a descending order. And then I'm going to take top 5 of them, for example. And then I can print each one on a separate line. Okay. And now we have top 5 CPU spenders, and you can immediately tell that the winner is way busier than the runner-up, and therefore this process here has got to be the cause of our problems. Right? So we were quickly able to find the process causing our problems. Now we're going to find out a little bit more about it. So I'm going to take it into a variable, into a PID variable. I just need to replace this. And now I can ask my runtime something about this process. For example, I can ask about current stack trace. Stack trace, okay. And now I can immediately tell that it's doing something in a cowboy and in plug, so it's a web request and it's in a demo router and the operation is sum, the file name, the line number, and now this gives me already a lot of info so I can go back to the code, stare at it, contemplate, meditate a little bit about it and maybe some idea comes. But why should I stop here, when I can do so much more than that? What I can do is I can trace the activity in this process alone and think about it. You have like thousands or millions of things running around your production and you can point to that one and you can find out what happens in that particular activity. And this is what I'm going to do. I'm going to trace the activity in this process. So there are a bunch of different ways how you can do this. I'm going to use a fairly low level but out of the box available module called DBG. Don't be intimidated. It's a little bit gnarly and arcane, but does the job. For real thing in production, I wouldn't really recommend DBG, but it's quite useful otherwise. So I'm going to start the DBG tracer, and I want to trace this process alone. And in particular, I'm interested in function calls. You can trace a bunch of other stuff, such as garbage collections, messages being passed and received, and so on and so forth. But here, I'm just interested in functions being invoked in this process. And then I need to set a so-called trace pattern, so I'm interested in all functions, even the non-exported local ones of all modules. And this is going to generate a huge amount of output in this shell. Practically, it's going to block the shell. So I'm going to do a very cheap trick here. I'm going to sleep for a single second, and then I'm going to stop the DBG. Okay, so looks well from my end. Hopefully, it's going to work. And stop. Perfect. So we have 1 second trace of the activity in this particular process, and you can immediately tell that we are just recursing in this sum function. And now as a developer, I have a pretty good idea of what happened. Like in 99% of the cases, in my experience, the root cause of the problem is that I was trying to be too smart about too insignificant thing, and this backfired. So in this particular case, what I did is I implemented sum as a tail recursive function. So basically, I have 3 arguments. I have the start, the finish, and the currently accumulated sum. Every time I recurse, I increment the sum and I increment start by 1, and I'm going to stop when start and the finish are the same, which is clearly not going to happen for any negative number, floating point, and so on and so forth. A bunch of different edge cases I didn't consider, but now I know what the problem is. I can go back to development, fix the problem, even redeploy without needing to restart the system. But meanwhile, this thing here is still running, right? So we're still burning our CPU. And I can do a little bit to help this production. I can stop this particular process. I can send it an exit signal. And in particular, an exit signal is arbitrary atom, but I'm going to use a special atom called kill. This is special because it cannot be trapped. It cannot be intercepted. This is kind of like kill -9 in Beam world, if you will. And as soon as I do this, the process is forcefully terminated. Going back to the observer, the scheduler utilization falls to normal. Now what you just witnessed is I approached the running system and I was able to quickly sift through thousands or maybe millions of things running around. I was able to find the rotten piece, dig into the rotten piece to find why is it rotten, and then pull it out without disturbing anything else. And this kind of level of service makes me a very, very happy user and gives me a lot of confidence that I can really deal with my system, when some things go wrong, which inevitably is going to happen. And I'm not aware of anything that comes even remotely close to giving you such kind of level of service. Like even this, seemingly simple functionality, the ability to forcefully terminate a process, an activity gone rogue, which refuses to cooperate, is going to be mission impossible for the vast majority of other so-called Erlang alternatives. Like the best case they're going to give you is something along the lines of this. So Yeah, you will basically, you will only be able to politely ask the thing to stop itself and then hope and pray that this will happen, which of course is not going to be the case for the example you have just witnessed. And then your best and only option is to restart the entire operating system process, thus taking down thousands or maybe millions of perfectly working, fine, healthy activities as a collateral. And in my opinion, that's pretty shitty. Now, Beam is of course way more, gives you a lot of more options because you can talk and work with your runtime, right? So I can do this thing also. I can ask the thing to politely stop itself, thus giving it a chance to do some final cleanup, say some final last words. But I can do more than that. I can first ask my runtime to let me know if the process terminates, right? So this is the process monitor. Then I'm asking the process to stop, and I'm waiting for the so-called down message, which I'm going to receive if the process stops, no matter why it stops, because it can also stop because it crashed before my message even reached it. And I'm going to know about it, and I'm going to be able even to distinguish the reason why it stopped, right? So that's one big guarantee. Another thing is that I'm a separate process, right? So I have my own lifeline. So I can wait for, say, 5 seconds, and if I don't get the down message, then the thing refuses to stop. Maybe it's super busy, maybe it ignores me, and I'm going to brutally kill it. And because the exit signal is asynchronous itself, I'm going to wait again for the down message, but now I can count on the fact that it's going to happen. It's going to come up, almost instantaneously. So this is a sketch for please stop yourself or die brutally pattern. Of course, you don't have to write this. It's included. Usually, you don't have to write it. It's included as the part of the supervisor OTP supervisor abstraction. Another thing that we can do working with a runtime is performing some task with a cutoff time, with an upper time limit. Right, so let's say we have to do some job. The boundness doesn't matter here, I/O or CPU. So I'm starting the job in a separate task, and this is a separate process. Right, and then I'm waiting for the task to arrive, for the result of the task to arrive. So this is task yield for at most 5 seconds. So if I get this result, then I can do something useful with it. Yay, good for us. If not, in 5 seconds, then tough luck. I'm going to invoke task shutdown with the reason brutal kill. Under the hood, this is going to do what you've seen on the previous slide. Process exit with the reason kill, followed by waiting for a down message. And now, as a reader, when I'm reading this code, there are some facts of life, dogmas, if you will, that I can count on. So this thing is going to run roughly about 5 seconds. It's never really exact, but somewhere in the area, unless the system is, of course, super overloaded. And once this piece of code is done, in the next expression, I can be certain that this computation is not running anymore. This is the fact of life for me, and it completely removes some possible hypotheses from the table when I'm reasoning about my code. And all of this is possible. Everything you have seen, starting from the demo, the previous demo, all the way to here, is possible, first and foremost, because your activities are first-class runtime citizens, entities with identities. Finally, I want to talk a little bit about shared nothing concurrency. So this is a fairly famous property. I usually like to describe it as the fact that these processes are really separate programs. They just happen to be running in the same operating system process, that's all, but they really have nothing in common. They have like their own separate execution paths, they have their own stack, their own heap. They might even have different versions of the same module. So really nothing in common. Now, this is a great example of a trade-off being made in the implementation of Beam. So because we have this complete shared nothingness, this means that you have to pay the price when those things communicate. When you're sending messages are usually deeply copied. There is one optimization exception, but otherwise they are mostly deeply copied, and you pay the price, right? This is temporary memory allocation, and this is some time. It requires some time. But a nice thing is that this price is explicit. You pay it upfront, it's visible, and whenever you tune and bench your system, you're gonna count on this thing, and you're gonna usually optimize your messaging protocol. You're going to avoid being overly chatty between processes, and you're going to avoid sending needless pieces of data across process boundaries. Now, a nice thing about all this is that by paying this price up front, you avoid a surprising and sometimes very expensive price of stop-to-world garbage collection. So there's no such thing in Beam world. Processes are garbage collected separately. And what this means is when you tune your system, when you reach some desired performance numbers, you can expect more consistent behavior in production, less surprises, less gotchas over time, and this is always nice when you want to reason about your system. Another thing about this shared nothing property is that everything somehow belongs to a process, right? So process has its own memory, but it is also a owner of resources. And by resources, I mean stuff such as file handles, network sockets, CTS table, traces, monitors, and so on and so forth. Everything belongs to some process. Like if I open a network socket, then I'm the owner. And I can give the socket away to you, and then you're the owner. But somebody is always the owner, and that's the main idea. Now, with this in mind, when a process terminates, then everything is properly reclaimed, so memory is released and file handles are closed and sockets are closed and so on and so forth. Even if the process is terminated forcefully, and you always have to think about this case, like if I'm terminated brutally, I don't get to say final last words. I don't get to try catch or try after something. I don't have the time for that anymore. But still, whatever I own is going to be properly reclaimed, like those files and sockets. Okay, so finally I want to talk about how OTP ties up and somehow builds upon these seemingly simple low-level guarantees to provide some guarantees of its own. In particular, I'm going to talk about the supervision tree. So these OTP supervisors, they are frequently mentioned in the context of restarting failing activities or failing processes, and this is arguably one of their most important features. But another important feature is this idea of the supervision tree, which basically allows you to take this pile of thousands or millions of processes and organize them into a hierarchy of services, of sub-services, of microservices, nanoservices, picoservices, and so on and so forth. You can think about it as something like an init-d system for your beam. It's just a top-down view. So this thing here is an example of a supervision tree which I used a couple of months ago at my city when I was demoing Phoenix. So I have like a top-level supervisor, which is system, and the system consists of a backend service and a front-end service. So when I start the system, we first fully start the backend service, then we fully start the front-end service, and so on and so forth. So that's the general idea. Now, for various reasons in this kind of a system, I may want to stop some parts of it. There are a bunch of different reasons for this, whether it's for fault tolerance, or maybe it's just for your own logic, especially in distributed systems, or maybe when you're doing some hot code upgrades, so you want to just restart some part of your system. There are a bunch of different scenarios, and this is not an unusual case. Now, say that I want to stop front end. This is what I would expect to get, right? This kind of seems intuitive, and this is what you're gonna get if you have a proper OTP supervision tree, because OTP supervisor is gonna give this to you. It's gonna make some guarantees, but it doesn't happen by chance. It happens because OTP sits on top of these seemingly simple properties. In particular, frequent context switches and preemption means that even if all the workers are completely busy and gone berserk, the supervisor as a separate process can still do its work and terminate them if needed. And then having activities as first-class runtime citizens means that supervisor can work with its runtime. First, to ask the runtime to be notified when things terminate. Secondly, to ask the runtime to forcefully terminate the activities that refuse to stop. Finally, share nothing concurrency, in particular, the ownership of resources and memory means that whatever you stop, whatever you terminated, no matter how you terminated, it's going to be properly reclaimed and released. Now, if you take any of these properties away, pick either one, take it away, and things might work in many simple cases, but there will be some completely non-obvious and very nasty problems lurking around. You might end up with unstoppable processes, which might lead to dangling processes, and that might lead to race conditions and re-entrancy and needless memory consumption and needless excessive CPU consumption, which in turn might degrade your performances significantly. Your system might not be able to properly self-heal in all the cases, and sometimes the attempt to do so might actually aggravate your problems. Basically, your fault tolerance layer becomes itself faulty, and in my opinion, this is pretty terrible because fault tolerance is, I believe, one of the most important property of any kind of a software system. Now, of course, if you are aware of these deficiencies in your runtime level, then you can work somehow around them. You can improve your chances of things going well, nothing going wrong. So you can invest in some best practices, code reviews and whatnot. But no matter how hard you work, how much effort you invest, you will never be able to fully eliminate those risks because they originate from within your runtime itself. And this leads me to the main point of this talk. So it is my impression that as the community of software developers, when we're considering our tools for the job and when we're comparing different tools and discussing them among ourselves, that we tend to put a huge amount of emphasis on these properties here. And sometimes watching all those considerate, open-minded and polite people on sites such as Hacker News or Reddit, I get this feeling that like a success and reliability of a software system depends on whether you have curly braces as block delimiters and semicolons as statement delimiters and out-of-the-box one-liner deployment commands, one size fits all. So I'm not going to say that these things don't matter, right? Of course that we want to have some reasonable and uniform language syntax so we can actually reason about it, and we want to have quick onboarding experience, and we want to have a rich ecosystem so we can actually focus on our core challenges. These are important properties. But if they sit on top of a runtime which is not built for the kind of software that we're building ourselves, then essentially they are just a hollow shell, just a shiny facade, hiding a shaky and inappropriate structure. Now, in contrast, if your runtime is properly built for the kind of software that you're building, then it is perfectly possible to evolve, support different syntaxes, and to flatten out the learning curve and to evolve your ecosystem. It's going to take a lot of time and effort, yes, but the road is straight ahead. You never look back. You never need to reconsider or regret your past choices. And of course, a great example of this in practice is itself Elixir. The thing is that your runtime is your foundation. It is your ground. And when your ground is solid, then you can move on top of it with a lot of confidence at a steady, reasonable pace, and you can start building your system and confidently watch them grow and evolve way beyond your original plans and imagination. And this is why I would say that when choosing your tool for the job, especially if the job is the job of building a software system, then ask not only what your language syntax and your libraries and frameworks can do for you, but first and foremost ask what your runtime can do for you, because it can make a huge difference. Links for those who want to dive deeper. I have put this presentation online. It's already there, so you can grab the links there. And this was pretty much all that I had prepared for you, so thank you for your time. Okay, do we have time for questions?
Yeah, I think so. Yeah.
Okay. Yes?
So in OCP 20, in the change notes, it said that they're no longer copying Erlang primitives or literals. How does that impact on the shared nothing concurrency?
I treat it as an implement. Okay. So the question is, in OTP 20, they're not gonna. They announced that they're not gonna copy. What did you say? Erlang literals. Yeah. And the question is, how does that affect shared nothing property? So the shared nothing is a semantic property. You know, the fact that internally some things are actually shared isn't just an implementation detail. The same thing already holds for binaries. So the shared nothing property is still there. Yeah. Any other question? Oh, we have there. Yeah.
Is there any effort being made to improve support for handling reductions in NIFs or other natively compiled libraries?
Is there any other effort to support handling reductions and NIFs in?
Yeah. Inside NIFs and stuff like C code or something that interacts. Is there any work being done to improve?
Well, there are definitely dirty schedulers, right? So you can use that if you have long-running NIFs. They are being officially supported since Erlang 20, right? Yeah, and as far as I know, even garbage collection, as far as I've seen, will run on dirty schedulers. Is that right? Yeah. That's announced in the release note anyway. So that means even less possible scenarios where you could have longer a single case of a single process grabbing a scheduler for a longer time. So that's as far as I know that is going to happen. Yes.
Besides DBG, what other sort of tracing and debugging tools would you recommend?
Well, I would definitely recommend first and foremost a tool by Fred Hebert, which is called Recon, precisely. Yeah, so that's still a command line tool. You have to install, you have to add a dependency to your project, but it has some safeguards. So you don't blow up your production with DBG. It's kind of easy. If you overdo it with tracing, then you might end up with doing a denial of service against your production, and you essentially need to restart. Recon has, all the pieces in place that you don't do this. It also has a bit higher level wrappers. Other than that, of course, Observer is your basic thing. There is a web observer, and in those links you will also find, I think it's fairly new thing, this Erlang Performance Lab. This is being developed by Michal, I believe, from Erlang Solutions, and this is also one thing that tries to visualize. So there are a bunch of different ways how you can visualize this stuff, because you can get them programmatically, and then it's, in theory, just a matter of drawing some nice graphs. But I would start with Recon, and I have it even in links, so I would first and foremost start with Recon. Okay, oops. Any other question? Yes?
Do you know if there is a text version of the process map that you would get in Observer that you'd be able to run in iOS to see a map of the process of the supervision trees?
Is there a text version of what is a process map? What do you mean?
Yeah, so in Observer, you can see what the supervision tree is.
Is there a text version of a supervision tree?
If you're in a system where you can't run Observer easily, is there a way to get?
I am not aware that there is a text version of a supervision tree, but you can usually, if you have an SSH access to a machine, then you can get an observer through an SSH tunnel. Otherwise, you can consider web-based observer. So that's one other possibility. Maybe there actually is, but I haven't encountered it. I have used of the text kind of observer-like tools. There was one which was called NTOP, which is a bit more elaborate version of ETOP that already exists in the distribution, but that thing didn't give you a supervision tree itself. Yeah. Okay. Any other question? Okay, thank you.